Okay, so a bit of a recap and a preview for next week's activities. Okay, so for next week, may I remind you that we will have the second midterm on Wednesday, okay, in class. So that's next week on Wednesday, and the midterm will cover till last week's lectures. Okay, last week we had both Wednesday and Thursday for lecturing, right? So the lecture part will be you need to review the lecture till last week's lecture. So that means that next week's midterm will not include today's lecture. Okay, let's be sure on that. But it will include the homework content for homework number 5, and we will be discussing homework number 5 tomorrow, okay, as usual. So that's the plan for this week and next Wednesday. And next Thursday, since Wednesday will be the midterm, so I will also want to use Thursday for finishing a lecture, probably lecture 11, which we will start today, okay? So that's the plan for this week and next week. And about recap, so let's kind of think about what we covered last week. So last week we introduced the idea that if we set g of n is equal to -1 to the nth power h of n, where h of n is a low pass. It's an impulse response for a low-pass filter. So simply by doing this, simply by changing the sign of every other sample, okay, let the polarity alternate, 让它变成交错啊. Simply by changing the sign right here for every other sample, -1 + 1 -1 + 1, right? So we can transform a low-pass filter into a high-pass filter. Okay? The idea is that if you go to frequency domain, you can show that if the low-pass design is like that, with a let's say corner frequency at omega cutoff, then after this transformation, if this is h of omega, then g of omega would be a shift of the spectrum by pi. To the right or to the left, doesn't matter, because by pi is the same. The result will be the same. Okay? So let's say we just move. So that means the pass band is going to be now centered around Nyquist frequency, and it goes backward like that. So now the cutoff frequency, this width, so the cutoff frequency becomes pi minus omega c, where this is the Nyquist. So this is pi. This is the frequency axis. Okay? This will be g. So last time we said that now we don't need to, we know how to design a high-pass filter by first designing a low-pass filter. Okay, so so this is really, really simple. Okay, and furthermore, if you know how to design low-pass filter, you know how to design high-pass filter now. Next, you already know how to design a bandpass filter. Okay, a lot of time we want to just keep in the frequency domain. Let's say we want to keep the content from omega cutoff frequency 1, cutoff frequency 2. Okay, we want to keep the frequency, the passband, to be in between two cutoff frequencies, one at the low frequency side, the other at the high frequency side. So I would suggest that one possible way of doing it, is to design a low pass that cuts off right here, and then you can also design a low pass that cuts off right here. A high pass, I mean, yeah. So this is G, and this might be H. And each of them would correspond to a difference equation, right? So now you can concatenate, put them in series, okay? When we put them in series, H of Z, G of Z, then the result, the entire system, is a bandpass filter. Okay, this becomes a bandpass filter just by putting them in this, the order doesn't matter. You can use first H, then G, or first G, then H. Doesn't matter, okay? Because the frequency response will be a product. The frequency response is 相乘, will be a product, okay? A product of H and G, okay? So we know how to start with now you know how to start with a low pass, and you know how to design a high pass, and we can put them together in series, you get a bandpass filter, okay? So that's one topic last week. And last week we also had another topic. We also had another topic that's called all pass. So the idea is that we began our discussion by thinking about the situation when we have one pole and one zero in what we say reciprocal locations. Reciprocal locations, that means that if the pole's distance to origin is r, then the zero's distance to the origin is 1 over r. 1 over r with theta. Okay, let's say they are arranged at the same angle on the z-plane. Okay? Same angle on the z-plane. And if their distance to the origin are reciprocal to each other, r with 1 r for this and 1 over r for that, then we have shown last time that the magnitude response of this system, and the magnitude response, if we denote the pole by p and the zero by q, then when we define h of z as 1 minus p z inverse, 1 minus q z inverse, having 1 0 on top, 1 pole at the bottom, right? Pole at p, 0 at q. So we've shown that, turns out, the magnitude response will be a constant. If I remember correctly, the constant is 1 over r. I might be wrong. Yeah, it's a constant. The key point is that this is a constant. The magnitude response is constant. And we didn't show that the phase response will always have a negative slope at every frequency. At every frequency, the slope of our phase response is always negative, which means that equivalently, the group delay is always positive for every frequency. Okay? Whatever system that passes through, whatever signal that passes through this system, the group delay is always going to be, for all frequency components, group delay will be positive. Okay? And so that's a property that I put in homework number 5. I included it for homework number 5 for you to mathematically derive that this is true. Okay? This is homework number 5. So please take a look. So in homework number 5, I suggest that we can reach this conclusion through bilinear transformation. Okay, through bilinear transformation. So the key idea for homework number 5, maybe I can say a few words. The key idea is that we put the pole and zero map, put this map through the inverse of bilinear transformation. Bilinear transformation originally is to express, when used in a forward way, when we designed the Butterworth filter, we used it, right? So we expressed S as a function of Z, but now we use the inverse function, Z as a function of S, but it doesn't, so that can be, you can do that because bilinear transformation is bidirectional, okay? It's invertible, right? Basically invertible. So put it in through the inverse of bilinear transformation to go from Z to the, no. Wait. Z of S. No, S of Z. Indeed, it's S of Z. S of Z. Right. So to go from Z domain to S domain, it turns out that P and Q now becomes, I asked you to show, they will be on two sides of the of the imaginary axis, right? You have already learned that the inside of the unit circle, corresponds to the left-hand side of the S-plane, right? So turns out that you will find that pole goes here and 0 goes there. And they have equal imaginary part on the S-plane. So basically, you can show that, okay? I asked you to show that. So from there, it's first, you can also see that why the magnitude response, now when you go along the imaginary axis in the S-plane, the magnitude response is a constant, while the phase response will always have this nice property that its slope is always negative. Okay, so that's kind of a preview. If you haven't taken a look of homework number 5, please do that. Right? Okay, so so that's part of homework number 5. Right? And so today, I would first like to offer you an alternative proof of constant gain, the property of having constant gain when we have 1.10 at reciprocal location. Okay, an alternative, 另外一种的, 另类的, an alternative proof of the same property, still the same property we're talking about. It turns out that last time we just checked this equality. 我们检查这个等式嘛, we checked this equality simply by algebra, by just replacing z with ej omega and do some massage, do some morphing, then we can reach this conclusion for sure. So that's using algebra. So, but this time, again, I would like to introduce a geometric interpretation, 几何的解释, geometric interpretation, why when we go around, we let the frequency increase and let the omega, let z to go around the unit circle like that, turns out that h of z, you can use geometry, use high school geometry to prove that the ratio is always 1 over r. Okay, so we'll begin with that. And today, we will also, let me just say by word, okay? So today we will also start a new lecture about filter structures. We will be drawing schematic diagrams, flow charts of signal processing, okay? Let's say when we implement a filter using a difference equation, you can make a plot, make a system diagram for which contains delay and summation and multiplication, okay? Multiplier, summation, as well as branching and delay. So you can use these building blocks to construct a filter, okay? So we'll start this new topic. And this new topic is important because then we'll have a more detailed discussion on computation efficiency and so on, okay? FIR versus IIR, right? So we'll go to that the next lecture, okay? So, all right, so any comments so far? Is everything clear? Yeah. Okay, so let's come back to the lecture note. Lecture number, which lecture we have? We have lecture number 10. Yeah, okay, good. So now, the geometric interpretation I was talking about, right? So we have shown that if, and I have changed my notation, now the pole is called P, okay? The pole is called P, and 0 is located at the reciprocal location. So now 1 minus PZ inverse, 1 minus 1 over P conjugate. That's where the 0 is located. That's the reciprocal location of P at the same angle, okay? Can we all see that P and 1 over P conjugate are at the same angle, okay? Are at the same angle, okay? All right, so that's our h of z. right here. That's our h of z, our system function right there. And then, so to continue, I would suggest that we multiply the top and bottom by z. Okay, can we do that? Yeah. When we multiply the top and bottom by z, and suddenly we have the ratio of z minus p to divide z minus q, basically. Okay. This q equals to 1 over p conjugate is the location of the 0. And we are going to say, yeah, so this is what I said. Let's have a polar representation of p, polar representation, 极坐标, polar representation for p with radius r at e, j, theta, theta being the angle. Okay, theta being the angle. Yeah, let me refer to my cheat sheet. Okay, yeah, so we are going to assume that P may occur right here. Let me still use black. Yeah, P is right here, and we have a straight line with an angle theta, okay, and the radius r. And then we have 0 somewhere right there. Let's say 0 is called, this is called P, this is called Q. Okay, point P, point Q. And 0, so Q. Yeah, so with our definition, our representation of P by its polar coordinates, then 1 over P conjugate is 1 over R E J theta. Can we all agree on that? Okay. It's pretty straightforward. Okay. No doubt about that. All right. So now with this, let's take a look of what's going on right here. Let's take a look at what's going on right here. Okay. Here in this expression, we have we divide one complex number with another complex number. We divide the top, which is a function of z for sure, with z minus p. So both of them are functions of z, and we have the situation of dividing one complex number by another complex number. What happens? What will happen? We know that when we divide two complex numbers, their lengths divide, right? And their angle subtract. Now we take the difference of the angle and the ratio of the length. Okay, so that's what's going to happen. So therefore, we know that especially when we evaluate this ratio, we want to we have to think of the top part as a vector, and this vector is z. So now when z is evaluated on the unit circle like that, with omega being a parameter, omega is going to around the unit circle. Okay. Z is going around the unit circle, omega, that means, omega is from minus pi to pi. You know that. So let's just randomly find an omega. Okay, so for this one omega right here, this is the angle of omega. And z is right here. Z equals to ej omega. Now, so when you look at z minus p, that's a vector. That's a vector pointing from P to Z, right? This is a vector that points from P to Z. Can you all agree on that? Z minus P, right? Is a vector pointing from P to Z. So Z minus P is one vector. Z minus P is one vector that points from P to, that points from P to Z. So that's a vector right there. That's Z minus P. Keep that in mind. And similarly, what is Z minus Q? On top, here we have Z minus Q, right? So similarly, it will be a vector that points from Q to Z. From Q to Z. So this is the other vector, okay? yeah. Let's say, yeah, let me put explicit, this is the vector of z minus q, okay? All right, so now the magnitude response, therefore, the magnitude response, when we write down h of e j omega, that is to evaluate h at, when we just substitute z with ej omega, right? In that expression, we substitute z with ej omega and see what happens. So now we have ej omega minus q. Actually, I think I can just say q. Yeah. Divided by ej omega minus p. And when we further consider its magnitude, we put an absolute value around all those the expression, right? So we want to show that now we want to show that this is a constant. Is it a constant? That's our question. That's our question right here. Yeah. So what do we have? So now we also understand that since we are dividing two complex numbers and take the absolute value, essentially what do we have? We are talking about the ratio of two lengths. We are talking about the ratio of, let me put that, let's say if this point is denoted as S, okay? If this point is denoted as S, then we are talking about dividing SQ, the length, with SP, the length, right? Can you all see that? The magnitude response, when this point S, okay, when this point S goes around the circle, it goes around the circle. This S, when omega changes, yeah. The magnitude response is going to be equal to the ratio of two lengths, SQ divided by SP. And S is moving. S is moving around the circle. Okay? So here, S is moving around the circle. So can we see that now I invite you to look at this figure and tell me that there are two triangles. So now we consider two triangles. Is that clear? Yeah. We consider triangle, if the origin is O. Okay, we consider the triangle OPS and another triangle OSQ. And I claim to you that these two triangles are similar. Why? Because, first of all, these two triangles share a common angle. 它们有一个同样角度, right? They share a common angle, yeah, which is the angle of SOP equals to the angle of, you name it, QOS. Yeah, I think QOS. That's basically the same angle, which equals to what? To omega minus theta, if you will. So there's a same angle. And then please also notice that, and let me put a comma. And we have they are similar in that their size is subject to a scaling. Their size is subject to scaling. If you notice that OP divided by OS is, of course, equal to R divided by OS is the radius of the unit circle, right? So OS is 1. The length of OS is 1, right? And that, I claim, equals to OS divided by OQ, which is equals to 1 divided by 1 over R. Yeah, so that's why these two triangles are similar. 相似三角形 We have two similar triangles. Just simply by checking the ratio of their size, their sides, okay, the ratio of the length of their sides, and just by noticing that they share a common angle. Okay, so we have proven that these two triangles are same shape. Just you need to flip one to get the other, right? You need to flip one. You need to somehow kind of flip the triangle like that to get the other. Otherwise, they have the same shape, exactly the same shape. And the order goes, I hope I'm doing this correctly. We start with the long side S here, SOP similar to QOS. Long side first, short side next, okay? Or I said short side first, OPS. This triangle OPS is similar to OSQ. Because they are similar. Why? Because we intentionally put P to be at a distance R, while Q is at a distance 1 over R away from the origin. That we intentionally, 我们故意的 on purpose we put OP and OQ at reciprocal locations. So no matter how, now you change to the next omega. Okay, now S moves. Doesn't matter. When you move S to the next location, you still have the same result. When S now is moved to another place, now OS becomes this, and QS becomes that. And you can still consider the same thing that we have the triangle of OPS and OSQ. Okay, they are still similar. Okay, they're always similar, and it turns out that now the scaling factor is R. The scaling factor is R. Okay, similar with the scaling factor of R. So that means therefore we reach that the third side. So we have considered the ratio between OP and OS and between OS and OQ. So we must also conclude that the third side, which is OPS, OPOS. I'm a little confused. We have OPOS, now it must be PS. PS divided by SQ must be equal to R. And that finishes our derivation. So we have found that now you have found that PS divided by SQ being the ratio of the third side of those triangles must also be equal to R. So therefore here the magnitude response is always equal to 1 over R. So that's that concludes our checking, okay, using a geometric interpretation. Okay, so this is something one small trick that I didn't find in the textbook, and I'd like to share with you because it uses. It's pretty nice. It's a pretty nice result. What else? So here we have shown the magnitude response is a constant, will be a constant in this situation. How about the phase response? Can we make some observation about the phase response and say something about it? Okay, so I challenge you. Okay, I challenge you now because now we can talk about geometric interpretation for the magnitude response. Can we talk about geometric interpretation for the phase response? Okay, so if you try that, so I'm just going to try it a little bit. Okay, so let's try it a bit. Let's try now. The phase response, what will happen for the phase response? should be equal to the phase of, it's going to be the difference between two angles. Yeah. The phase of ej omega minus q subtracted by the phase of ej omega minus p. So that's a phase response. The phase response, for you can also talk about a geometric interpretation. Okay. So if we blow up a little bit, we are going to talk. What we are talking about is the phase between these two vectors. Yeah. The angle between these two vectors. And this angle is, of course, going to change when S moves around the unit circle. Okay. Yeah. So you can ask yourself, does the phase, is this angle going to decrease or is it going to increase when S moves counterclockwise, in the counterclockwise direction? Okay. Yeah. When S moves in the counterclockwise direction, is this angle, is the angle between these two vectors, is it going to get smaller and smaller or what? So that's your kind of a nice exercise, okay? That's a nice exercise. Can we convince ourselves that indeed the phase response is monotonic against omega? Okay? When omega increases, is this angle. How will this angle vary? Yeah, the angle between these two vectors. The angle between these two vectors, because we know that's the phase response. Okay, so that there's a certain possibility you can also try to visualize what's going on right here. Okay, but anyway, in homework number 5, I suggested that we simply go to S domain. So that's yeah. I think I can end my discussion. Yeah, just to compare. 点点点 or blah blah blah. Okay, you can try to picture, try to visualize what's going on right here, or to compare. Please do homework number 5. Okay, do homework number 5. There will be a problem that specifically talk about the phase response of an all-pass filter when we move back to the S domain. Okay, it's easier over there. Is everything okay so far? So far so good. Do you rate this geometry interpretation 1 to 5? Okay, yeah. Rate this geometry interpretation. I love geometry. Okay. All right. So I think that's much about what I want to say about this lecture, and yeah. So yeah, we have discussed. Okay. I think maybe I want to before we finish this lecture. I feel like that last time I didn't do a good job in motivating why do we need to study all-pass filter. Okay, so there's one missing topic. So if you just go back to the top of this lecture of the handout, go back to the top of the handout. Okay, so let's kind of summarize what we have learned. If system has one pole and one zero in reciprocal locations. Okay, reciprocal location, 1r for p and 1 over r for q. Okay, and then we have shown in multiple ways that the magnitude response is going to be a constant, and therefore we call it an all-pass filter because every frequency receives the same gain. Okay, that's why we call it an all-pass filter. So that's the reason for the name. But this year we will not go through the details here, but I would like to just simply mention, I promise this will not show in your test. Okay, yeah. In the textbook, if you're interested, in the textbook, it tells us about a possible way to make a decomposition of any causal and stable system. Okay. For any causal, essentially any causal and stable system, unless having 0 right on the unit circle, we can always decompose that system h of z into the product of an all-pass filter times something else. And this something else, this HAP is an all-pass, and H of MZ having this other part in this expression. The other part in this expression is called a minimum phase system. A minimum phase system, which is defined as having all its zeros and poles inside the unit circle. Okay, when the system has all its poles and zeros inside the unit circle, inside the unit circle, inside it, okay, inside. Now, when the system has all the poles and zeros inside the unit circle, the system is called minimum phase. Minimum phase, okay, minimum phase. So there is such a decomposition, okay, and it turns out that because an all-pass filter, okay, we can talk about this a bit further. Because an all-pass filter always has a positive group delay, right, for every frequency. So equivalent to that means a minimum phase filter is a kind of filter that has the minimum phase delay, minimum group delay, among what? A minimum phase filter has the minimum group delay among all filters that share the same magnitude response. Okay, 有点长哦, So there's such a discussion about it's almost always possible to decompose any given system. As long as it's causal and stable, we can formulate it as a product of all pass and minimum phase. Okay, where minimum phase is where all pass has a positive group delay, and minimum phase has a property that this system, this part, has the shortest group delay for every frequency among all possible filters which share the same magnitude response. Okay, it's a long story, but some people find like a practical usefulness. Okay, find this decomposition useful for certain design. Okay, and the key idea is that all pass filter. When we call this, the key idea is about a filter. Let me show you a buzzword before I finish this lecture. The key idea here is filter invertibility. Invertibility of a filter. Can we find an inverse system that kind of compensate everything for any given system? Okay. Let me say that. Okay. So when we have a system somewhere, and it processes our signal and system, right? A system processes a signal, right? Now the signal becomes a different signal. But can we construct a second system that does the opposite, that undo whatever processing that the first system does to our signal? Can we undo a process? Can we undo a process, the way a system processes a signal? Can we undo it? When we move backward and we go backward, that's undo, right? Now I'm back, I'm still myself, okay? Now, can we undo an action? Right? And if we can undo an action, then we say this filter or this system is invertible. Okay? Is invertible. Okay? Yeah. So conceptually, invertibility. Yeah. Maybe let me say a few words about filter invertibility right here, down here. Okay. Yeah. So there's some supplementary remark about system invertibility. You actually have seen a few examples already. Okay, so remember that, for example, a few weeks, last month, we said that for example, if h of z, I remember we have this example. If h of z is 1 minus 1 divided by 1/2 z inverse, okay? And we know that its impulse response is infinite. This is an IR filter, causal, okay? So h of n, by now you know it's going to be right-sided, and with a factor, it decays by a factor of 1/2. So this is our impulse response. So once you process the signal with the system h of z, and the result yn is equal to x convolved with h, right? We know that. The question is, can we invert this? Can we undo h? Can we undo h by? Can we undo it? Okay, and the answer is yes, we can. So simply define g of z to be equal to 1/h of z, and in this case, it's simply 1/1/2 divided by z inverse. Okay, which is an FIR. And I believe that in one of the maybe follow-up discussion session, we have talked about that indeed when we then just when we put y through g, when we put y through g, let's say the result is you name it. Let's say it's y2 of n, okay? y2 of n now equals to y of n convolved with g of n, which has only 2 samples. And you can show that the result is indeed equal to x. Okay, so here's the whole picture. We have x, and it is processed by a system h of z. And then we undo the process by putting the output again into a second system, so that now the result, when we convolve the output with this new system's impulse response, we get back our x. We can recover x. We can recover x in, not only we can recover x, but in a causal and stable way. Okay, in a causal and stable way, where here g is causal and stable. Right. So this is about the topic of all-pass minimum phase decomposition, people call it. For any system, when we decompose it into an all-pass and a minimum phase, turns out that because minimum phase system, when we go back to the top, because minimum phase system has all its poles and zeros inside the unit circle, therefore, if we call this h of z, containing poles and zeros all inside the unit circle, then when we invert it, when we take 1/h, poles become 0 and zeros become poles, right? When we put h versus 1/h, right? 分子变分母，分母变分子嘛，The denominator becomes the numerator, then the numerator becomes the denominator in terms of the two polynomials. Therefore, poles become 0 and 0 becomes poles when we invert h of z. Okay, so the inverse system still has all the poles and zeros inside the unit circle, and therefore is stable. Okay, it can be implemented in a causal and stable manner. So this is a very nice property. A minimum phase system has 2 nice properties. First is group delay is shortest at all frequency among all the filters that share the same magnitude response. That's the first property. The second property that is causal, and it can be inverted in a causal and stable manner. This is a long story. Okay, so I want to just tell you that this will not show on the test. Okay, but if you're interested, there's a long discussion on the textbook about why we find all-pass filters to be a nice concept is a really nice concept, and it can have certain applications in terms of inverting a system. Okay, inverting a system. Right. Okay, but because of time, maybe we can take a 10-minute break. Okay, when we come back, let's start lecture 11. Yeah.可以帮我准备杯水啊？啊。
后面就是那个什么，就是这三张，就是把那个 IIR
好 OK yeah so starting this next lecture okay now we're going to change our topic a little bit. So for the past few weeks, we talked about designing low-pass filter using infinite impulse response or finite impulse response, IIR versus FIR. That's a big topic. Okay. So in the next, by the end of this semester, a kind of a key question we need to start asking is IIR versus FIR. Which one is better? For what purpose? Okay. So we need to talk about computation load. And we also need to talk about what? Maybe flexibility in your design. And we need to talk about this is subtle issue that we will cover next week, not this week. Okay. So it turns out that IIR, when designing IIR, there's a danger, so you have a risk, okay, of that could be caused by quantization of filter coefficients. Let me say that. Digital representation of filter coefficients this is a subtle issue, okay? So far we have discussed a bit about quantization. In what context? Does anybody remember? We have discussed quantization in a previous context. That is, quantization introduces quantization noise, right? And sometimes it sounds like white noise. In a previous homework, we talked about that. Okay? We talked about digitally representing all the samples using zeros and ones. Okay? But it turns out that we also need to represent filter coefficients with ones and zeros. In concept, they are real numbers, but we always have a finite resolution for any number we want to use in any computation, right? In any computation. It turns out that when we write yn equals to summation ak yn minus k, where k goes from 1 to big N, plus, let's say, plus summation bk. We've been using this notation a lot. This is a difference equation that you can design to suit your purpose. So summing k from 0 to big M, right? Turns out that all these coefficients have to be quantized in certain ways, right? Okay. So this is a subtle issue. Okay. We have said that FR filters are always stable, and I mean it, and that's basically correct. And we also talk about when we design IIR, we need to be careful. We want to put all the zeros inside. No, not zero. The poles, inside the unit circle, right? So next week, we'll cover the situation after the midterm when we come back, okay? When you come back, hopefully we'll talk about a situation, a funny situation. Let's say originally you go through an IR design, a Butterworth filter, right? And you have been able to place your poles somewhere inside the unit circle and they look good, except that some of the poles might be really close to the unit circle. Some of the poles might be really close to the unit circle. You may have zero outside or inside, doesn't matter, okay? You can zero here, zero there, zero there. Zero does not matter that much in terms of stability. But if some of the poles are really close to the unit circle, there's a danger. There is a danger that after coefficient quantization, when we represent the coefficients by 0 and 1s, the actual system is going to the poles of some of the poles might move outside the unit circle. Okay, so it turns out that the coefficient quantization might cause a pole to move outside in unexpected ways. 很难预料，而且很难预料. The bad news is that they got moved in unexpected ways, and we'll cover that next week. Okay? So, so this is a strong motivation why we need to consider study the structure. Turns out that to prevent this unexpected motion of displacement of the poles, we can avoid the problem by studying the structure, filter structure, by studying how we implement the filter using flowcharts. So in the next 2 lectures, we'll discuss that an IR filter can be implemented as if having for example, a delay line in the middle, and we allow the signal to flow forward and backward, like that. So this is the topic. I'm not sure. Have you learned this in signals and systems? 讯号系统有教这个吗？有吗？有？没有。Does this look familiar to anybody? Okay, that's good. Okay, sometimes I haven't. 电机系的课，我大概就是数学课，大概就讯号与系统没教过啊。Anyway, yeah. So that's why we need to study filter structures. So yeah, we need to study flow chart to enable such kind of discussion. What's the problem with each flow, and do we have other alternatives? Can we decompose the system into subsystems and put them in series or in parallel? So these are topics that will show up in our upcoming lectures. And one final thing is that in homework number 5, okay, I think if I remember correctly, I asked you to design a filter, the computer part. Again, I asked you to design now this time an FIR filter using the Kaiser window, right? Yeah, that's in your homework number 5. And I asked you to design basically to meet exactly the same specs. In homework number 5, again, we design a low-pass filter. But we have already done that in homework number 4, right? In homework number 4, we designed a low-pass filter, low-pass IIR filter. That's homework number 4. Number 5, we designed an FIR filters to meet the same specification. Cutoff frequency and transition width and so on, ripple tolerance. So it turns out that to meet you can compare, okay? So hopefully by comparing across 2 homeworks, you get a feeling whether FIR or IR, which one is more computationally efficient, okay? So we will continue this discussion, okay? And just my experience, okay, most of the time, I think almost always, when designing a low-pass filter, turns out the IR should be more efficient. Okay, computation load should be lower. I expect that. IR has a lighter computation load, so it runs faster. It runs faster on your computer or on any processor. Okay? But that being said, there's a famous way to accelerate FIR. So that's not the end of the story. I just suggested to you that in the most straightforward implementation, IIR is usually more efficient than FIR when we design low-pass filters, for example. Okay, but it turns out that that's not the end of the story. FIR has a secret acceleration gadget. Okay, there's the technique called FFT, fast Fourier transform, which can greatly accelerate FIR filters. Okay, so that will probably be near the end. Near the end of the semester, we talk about that. We will introduce FFT and their flowchart like that. There's also a flowchart of FFT. Okay, so we introduce that. So the 2 big topic is now this thing, as you will learn, is called direct forms. The direct form of IR and FIR implementation, that's one topic for this week and possibly next week. And after that, probably by the end of this month or the last week of the semester, last few weeks of the semester, we will talk about FFT acceleration. of FIR filtering. Okay, two important topics. And both are about filter structures. So therefore, the buzzword is filter structures. So with that, let me just jump ahead to my new lecture, lecture 11, filter structures. Okay, so in this lecture, we will learn to implement any LTI system, any LTI linear and time invariant system, which has now we are familiar that the system functions can be expressed in terms of the ratio between two polynomials b of z and a of z. And here are a few kind of the outline for this lecture. In this lecture, it turns out I think it's not that difficult. Okay, this is a rather this lecture should not be difficult, but you just need to kind of memorize the graphs. So that's kind of my suggestion. So you'll see a lot of graphs, and they are not hard to understand. But you just really, I suggest this for this the content right here. Spend some time to memorize the definition and to understand how the signal flows through the system. Okay, a bit about memorization. Right. So you will learn a few terminologies such as direct forms, and there are two kinds. It's direct form 1, direct form 2, and also for IIR systems. These two are simply merely for IIR. Okay. For IIR only, we can talk about representing our system in cascade or in parallel, breaking them into subsystems and put them in parallel or in cascade. Cascade is 串联, 串接, cascade or in parallel, 平行, 并联, and 串联. And on top of that, we also have what is called a transpose form. This is kind of funny thing, transpose form. And also then for these two are for FIR. It turns out that the FIR structure, as we'll see, will look like a ladder. It will look like a ladder, like 像一个梯子, ladder. Okay? The FIR structure will look like a ladder, and we call it a ladder structure. And since most of the FIR we talk about is going to be a linear phase filter, right? So we talk about linear phase. That FIR, after using Windows to design FIR, you get a linear phase filter as your outcome, right? So it turns out that if a filter is linear phase, that means that the coefficients have a symmetry. It's an even function. It's an even function around the center. Okay. So there is a simple trick to reduce computation load by considering this symmetry. Okay, so linear phase enable us to consider symmetry. We can consider the symmetry and reduce computation load. Consider the symmetry and to reduce the computation load. Okay, so these are the outlines for today's topics. So far so good? Okay, so let's now directly jump ahead to talk about our first direct form. Okay? So take a look at this system, right? When you take a look at system, can you tell me, even before you learn this, can you tell me what is the transfer function? What's the system function? The question is h of z with x being the input to your left and y being the output to your right. Can we write down h of z in terms of a ratio b of z divided by a of z? Can we do that? Okay, by merely inspecting this flow chart. Okay, by merely inspecting this flow chart. So yeah, we can give it a try. Why don't we give it a try? So here, let's start from here. So we have a branching right here, okay? So here, if it's easier to use the Z transform notation. So if the Z transform the signal right here, so note that the signal keeps coming in, okay? So for every new n, when n goes to n-1, a new sample, we obtain a new sample somewhere, okay? You want to think about this system like that. For every next sample, for every next n, when n increases by 1, we get the next sample. Okay, we receive one sample and produce this one. We will reproduce one sample to the right. Okay, so it turns out that it's easier to put things into the Z transform notation. So the signal right here after Z transform is denoted as big X of Z. Then here, right here, we should have what? We should have X of Z times 2Z inverse plus 1 right here, right? Because here is a bit of explanation. Z inverse corresponds to delay by one sample, okay? So let's say here is X of n. So we delay by one sample right here. What we have here is basically X of minus 1, or it corresponds to Z inverse X of Z, right? Same thing. In Z domain representation or back in the time domain. Yeah. Or back in the time domain. The inverse is one sample of delay, okay? Imagine you can hold the signal by one sample and let it show up one sample later, okay? So this is a delay, a delay component, okay? A delay component. So the output is simply the input you receive delayed by one sample right here. And here, when we put the number 2 next to an arrow, when we put a number next to an arrow like here and here, that means to multiply the signal with that factor. Is that clear? Yeah. Okay. So put a 2 around here. So that means right here after multiplication. So think of this as to produce a gain of 2. Okay. Multiply the signal by a factor of 2. So here we have 2 times x n minus 1, and then subsequently, 接下来啊, subsequently, we perform summation of this with this. There are 2 arrows pointing to this summation, right? We have 2 arrows pointing to the same summation. Therefore, we add them, and the result here, or it corresponds to really it corresponds to 2 times x n minus 1 plus x of n that directly, this x of n directly feeds all the way to the summation, and it comes out, and it shows up right here. Okay, is that simple? No, it's pretty simple. It's really simple. So if you will, let's define this as, it might be convenient to define this, the intermediate signal right here as V of Z, okay? Let's define this, denote it as V of Z right here. And now it's a bit trickier to the other part. So now we can talk about the next part. Now, let's focus on this part. Let's focus on this part. So I suggest starting from right here. Okay, we can start from right here. Okay, if this is y, then right here, what do we have? Right here, we have y of n minus 1, right? And right here, we have y of n minus 2, right? And right here, what do we have? Right here, we have yn minus 2 multiplied by minus 0.9, minus 0.9. And so on. And similarly, right here, after a factor of 1.5, right here, we have 1.5 yn minus 1. Okay? And there is a summation. So we add these two terms. The output here simply is the summation of what? 1.5 yn minus 1 minus 0.9 y of m minus 2. That's right here. That's right here. So you see, this is a kind of feedback, okay? So now we have a situation of having a path that connects the output, delay it, and scale the sample. When we sum up, it's fed back to this point, to this node, if you will. Okay, that's okay. So now for this node, we receive two branches to flow into this node. So we sum them. Okay. So we sum them. So it turns out that it should be easier to represent this as v of z plus y of z times what? Times 1.5 z inverse plus the polynomial minus 9, minus, not plus. So just simply be careful, you have minus 0.9 z to the minus square. Okay, that's what's going on in here. That's what's going on in here. But this equals to yz in the z domain. Therefore, we can kind of organize this. Okay? Therefore, we have y of z equals to itself times 1.5 z inverse minus 0.9 z. We have two terms right here, plus vz. And vz is what? Vz is here. This vz, now we can substitute vz with this expression. Vz related to the input by in a simple manner. Okay? So here we have xz of 1 plus 2z inverse. That's our system equation in the z domain. Therefore, finally, with this, we can just do a bit of rearrangement so that we can conclude. You're now ready to write down an expression of h of z. H of z is defined by the system function is yz divided by xz, right? So can we say something about this? Let me move things around a bit. 往下一点点. Therefore, what do we have? Therefore, it seems that we now have a final answer. Okay? Now we have a final answer. Yz divided by xz. Yz divided by xz should be equal to 1 minus 1.5 z inverse. That's the a of z part. And on top we have 1 plus 2 z inverse. Can we check that? Can you help check that this is correct? Can you help check that indeed? What do we have? Take a look. Take a look. We have y multiplied by a does it equal to x multiplied by b? All right? So I said that this is about you take a look at the analysis for one time and then you memorize. Okay? Then you remember next time you see the figure, please do not go through a derivation. That's what I'm suggesting. It's pretty simple. Yeah. It's not hard. Just need to be careful. Yeah, we just need to be careful. So so let's take a look in the graph. The graph we have, we are given a delay component and a factor of 2 right here. And the delay component right here to the right, delay component right here. Just pay attention. Contemplate under the flow diagram again. Okay, 就凝视它啊。Contemplate. Let's contemplate. Let's take a look of this entire diagram. We have delay components right here, right there. We have a factor of 2, a scaling factor 2, scaling factor right here, scaling factor right here. And with all the standard kind, whenever we have 2 branches flowing into the same node, we sum them up. That's pretty easy. Okay. So then you just put everything together, you see now, next time you can automatically make a translation, okay? Or you ask what? ChatGPT 4.0. Discuss this with ChatGPT 4 omnipotent, okay? Just automatically, yeah, this becomes, next time you are familiar, okay? You get familiar, right? Look at this flow diagram, yeah, it corresponds to this system function. And you can just make sure that this is true. Now, this is true. We have a causal system. We have a causal system where time proceeds in the forward direction, and we have delay line, right? So everything's causal here. Now, it's causal here, and this is the implementation of a corresponding difference equation. Now, we know that the result, when we relate the output with the input, this system is an IIR filter. It's an implementation of the IIR filter with several components, with 3 kinds of components: delay, multiplication, and sum. Okay, only 3 components are needed right here to implement an IIR filter. Yeah. Okay, so this flow way of implementation is so fundamental. Now we call it a sort of a direct implementation. We refer to this diagram as the direct form number 1. Okay, so it's a bit of memorization. Please memorize that this is called direct form number 1. Direct form of the first kind, or if you will, direct form Roman letter 1. Okay, 罗马数字1 direct form of the first kind. So if there's the first kind, there's the second kind. Okay, yeah. So this is only the first kind. So the next slide we show the second kind of implementation. But the idea, so let's take a first look. The second kind looks smaller, right? The second kind looks smaller, and I suggest to you that I claim to you that this is called the direct form number 2. And it turns out that we are still talking about the same filter, same transfer function, same system function, same h of z. But the implementation structure, the filter structure looks different. They look different, okay? But it's still the same transfer function. So how do we convince ourselves that these are the same? We're talking about the same filter. We may try. Let's try. Okay, let's try. Yeah. Let's try. Well, so here, if this intermediate, it seems that this is a bit more complicated. We need to start smart. Okay, we need to smart and call this an intermediate variable of w of z, which is the z transform of w of n. Okay, yeah. Let's try this. So if this is w of n, then right here we have w of n minus 1. Okay, which then branches 3 ways. Yeah, in 3 ways. It branches in 3 ways, in 3 directions. One to the right, one flowing downward, and yet another goes to. It branches 3 ways, in 3 directions, right? But no worry, when you go to the right, and there's in this path, for example, right here, then we of course we have 2 times Wn minus 1, right there. Okay. And similarly, right here, since we have a factor of 1.5, right here we have, we have 1.5 W of n minus 1, right there. And similarly, we still have, now we have Wn minus 2 after one more sample of delay. After one more sample of delay, we have, W with 2 samples of delay, and it goes to the left. And it goes to the left and is multiplied by a factor of that, right? So here we have minus 0.9 W of n minus 2, right there. And now the rest, we are left with just the summations, just the nodes which sum up all the branches, okay? So these 2 branches sum up right here, and you further sum up with what? With our input, okay? So we now know that here, right here, we have this node equals to x of n plus 1.5 of itself feedback and delay by 1 sample plus minus 0.9 itself delayed by 2 samples. That equals to W. Now we have an expression for W of n. That's the way we, again, after some simple but careful analysis, we found that this intermediate variable should equal to x plus 2 feedback terms. We have feedback right here, Yeah. Right? Is that clear? Yeah, we have the intermediate signal here itself can be expressed as the sum of input plus 2 feedback samples. 2 samples that got fed back to the node right here, and they sum up with the input. Okay. Now the rest here is actually easier. Here we can say yn equals to W of n simply plus 2 times W of n minus 1. Okay. So therefore, again, yz divided by x of z is what? Then we can make a kind of check that this is true, that yz divided by xz, when we go to the z domain, what do we have? Yz equals to 1 plus 2z inverse times W of z, right? Divided by x of z. But W of z divided by x of z is, you can figure that out by looking at this expression. Okay, maybe let me highlight it. Let me put a highlight right here. Okay, put a highlight right here. This tells you about the relation between W of z now is equal to x of z, what? Actually divided by 1 minus 1.5 z inverse plus 0.9 z minus square. If you when you become good at this, it's not that hard. You can see that. You can see that. And with this relation, we are ready to just organize everything in the final step. You can organize everything in the final step and say that indeed y divided by x is equal to 1 plus 2z inverse divided by 1 minus 1.5, 1 delay, plus 0.9, 2 delays, 2 samples of delay. I'm running out of space, but you know what I mean. Let me just improve my handwriting. Okay. Z inverse right here. Okay, I'm trying to just include, And this is called another direct form. This is direct form of the second kind. direct form 2. So same thing here, okay? Exactly the same system function. They're exactly the same with the previous page. The result what we have right here. They are exactly the same. But now, let's take a look and compare, okay? So next time you don't need to go through derivation. Just memorize, okay? Just memorize this shape, the entire picture, and how you will put all the checks that we have, wait. Yeah, just check that we have, that even though they look different at first, they result in the same system function. There are two different ways of implementing the same filter, the same IIR filter, okay? Yeah. So far so good? Which one do you like more? Yeah, if I ask you, which one do you like more? First one? Second one? Why second one? In Chinese, it's okay, yeah. 比较简洁, it's more concise. In what ways? 如果说它比较简洁, in what ways? 比较 compact, 就是东西比较少。只有2个 delay. Okay, that's a good point. Okay, yeah. Can we agree that the second one looks more like an Apple iPhone? Having look and feel 比较简单. It looks and feels more simple. Okay, right. So if you compare the number of delay components, right, the second one has only 2, and we enable that because the trick, yeah. But before I continue, some of you chose the first one, right? First one, anybody still? You like, you use Android phone? That's okay with me. Anyway, first one, why do you prefer the first one? If I have to say, I think the first one is called the first one with a reason, because it's easier for the derivation. It's easier to understand the first one, okay? So now the trick is really, this is about commutativity. Okay? Let me say that again. Commutativity. 交换, 可交换性. We know filters, LTI filters are commutable. It doesn't matter if you have the product of two systems. It doesn't matter which one goes first. Can we agree on that? The LTI system, because convolution is commutative. 折积这件事情是可交换的. It's like addition or multiplication. It's 具有可交换性, right? So because since convolution is commutable, when we concatenate, when we concatenate two LTI systems, it doesn't matter which one goes first. Okay? So the key trick is to now when we come back and visualize the direct form number 1, please visualize it as if we are concatenating two subsystems. One is the one on the right with this green box. That's one system, one subsystem. And the other subsystem, if you will, is this one with purple. This is the other subsystem. We have two subsystems. Both are LTI. Both of them are linear and time invariant, and therefore, you can feel free to exchange the order, to switch the order. Let's say it doesn't matter if x of n goes through the second system first, and then we extract the output and put it back to the first system. Okay, you can first. So that's exactly what's happening right here. Okay. What's happening at the bottom of direct form number 2 on the left here is what we have, the first subsystem. And then we just process x of n with this subsystem right here, right there, okay? Right there. Can actually zoom out. We process x with whatever that's here. And you move it now, you process x with that first. And then let the output which is W of Z right here, to go through the second subsystem. So that's a second subsystem right here. And smart enough, we can now merge the delay components. Do you notice that now with this change of the order processing, 改换顺序啊, when we change the order processing, going through the green one first, then the purple one, then the purple one. Turns out that now we can, the two of them can share their delay component. This one got combined with that and becomes this. Yeah. That's why the exact reason why we are able to place the delay line in the middle. Okay. Now the direct form 2 has a beauty of placing the delay line in the middle because they share. Because the two subsystems share the delay line in the middle. And that's a good thinking. That's good design. I like it. Okay, I personally really like it. The first time I saw this. Okay, this is possible because of commutativity of LTI systems. Right, 可交换性. So we have direct form number 1, direct form number 2. Okay, so the next slide is simply about making a simpler sketch. Okay, so now when we come back next week, right? When we come back next week, we'll be even more lazy. Okay, we'll be lazy as to just place. Actually, this is not even lazy enough. Let me explain. So now, next week when we come back, we'll simply put the word Z inverse next to this branch. Okay, so whenever you see a branch with Z inverse, that means a delay, one sample of delay, right? That will become our convention, and we have node 1, node 2, node 3, node 4, yeah, and we just place an arrow, any arrow still with a number, a scalar on next to it. That means a scaling factor, okay, and you can also think of Z inverse as a scaling factor in the Z domain. That's fine. And further, we are going to just, we're so lazy we don't even want to draw the summation component. Okay, there's really no need to draw that. 没有必要画啊，没有必要去画它. So instead, just let's try to agree that whenever we see two branches falling into the same node, that means summation. Okay, can we all agree on that? So that will make our sketch easier. Okay, whenever we see two branches flowing into the same node, right here and right there, two branches flowing into the same node, but not right here. This is one branch, one in and two out. Okay, so this is not a summation. Not a summation, because one in, two out. This is simply branching. Two out. One in, two out, not a summation, because it's one in, two out. But here we have summation and summation. Okay? These are summation. Because multiple branches flow into the same node. Okay? Yeah. So that's a kind of simpler way of drawing. So next time when we come back, we will be looking at the final figure looks like this. Now, indeed, we replace the delay branch with a Z inverse, a word Z inverse next to the branch. That means one sample of delay. And we have summation right here, summation right there. Okay? Yeah, it's pretty easy. As I said, this is a simplified plot that I hope that we can agree on. We will practice using this kind of notation. And then next time when we come back, we'll talk about how to break. So that will be after the midterm. Okay, after midterm, we'll talk about how to decompose an IR filter into subsystems in cascade or subsystems in parallels. And there are reasons of doing this. Okay, there are reasons of doing this. And where each subsystem, as you see, is a direct form 2. Okay? each subsystem right here is a direct from to here with delay lines arranged in the middle of the system. Okay. So we still have a few minutes left. Is everything all right so far today? Yeah. Okay, yeah, so yeah, I think I can end this lecture a few minutes early, okay? So please come back for tomorrow's homework 5 discussion. So otherwise, the class dismissed. Thank you. Yeah.